Okay, so I thought I'd do a video that explains how you turn basically motion from your hand into a channel change on a radio. What's actually happening inside the radio that actually changes channels. And what's changing that is programming from the channel selector switch to the PLL chip. So older radios, stuff older than this one, used to do what they called crystal mixing. You'd take two frequencies, mix them together to come up with the frequencies you wanted. When you changed the channel selector, you were actually switching in and out different crystals. When solid state got to the point where it was cheap enough to where they could use it in CBs, in the initial ones they had some kind of complicated ones. They're actually easier to work on because if you think about it, because most of the ICs were separate discrete circuits, but eventually they got down to the what I call the one chip wonder, where there's one IC pretty much handles everything as far as frequency synthesis goes. And that PLL is programmed. Now don't think of the programming as some big huge program like you would type out on a computer. It's nothing but ones and zeros. Yes, those scary ones and zeros. You watch movies about computers and whatnot on TV. You always see these big, huge strings of zeros and ones. Well, that's what's programming your PLL. Don't be scared by the zeros and ones. We're going to explain them. The zeros and ones are basically ground and voltage. A high, a low or a high. That's all it is. A zero is a ground or a low. A 1 is a voltage or a high. Now the voltage can vary, especially in more modern equipment. You can have 5-volt systems, 3.3-volt systems. It can vary from radio to radio, but that's going to be set by the equipment. But that's all that is, and you're basically just switching. You're either applying a ground to what's known as the program pins on the PLL or a voltage. But that's done with binary. Now that's, oh my God, binary. Mike, you're, yeah, I'm out. Don't. It's not that hard. I want to explain binary and explain it and show you how basically old school channel modifications actually worked. And actually how modern day modifications work with microprocessors, but instead of doing it with toggle switches, it's just done through programming, but it's doing the same thing. It's changing those ones and zeros that are being applied to the program pins on the PLL. So binary in a nutshell, we're going to do a crash course. So the first thing we need to know is what you're used to counting is known as the decimal system, which is a base 10 system. There are a few terms we're going to cover here. Base 10. Base 10 just means that for pretty much everybody on the planet, when you went to school, you learned to count. There were 10 digits that you learned, and with those 10 digits, you can make up any number. They are 0, and then 1 through 9. With those 10 characters there, you can make up any number. If you want to write 321 on a piece of paper, that's just what you write. 3, 2, 1. But you're using, these numbers right here, and that's it. And that's why it's called base 10. There's 10 characters, figures. I mean, shoot, you could use a screwdriver for 0, a spudger or pointer for a 1. You could use pictures. It doesn't really matter. This just happens to be back in history at some point, somebody created these 10 characters here, and this is what we use. Now, when it comes to electronics like this, they use what is known as binary. Binary is a base 2 system. There's only 2 characters. That's it. Now, there are advantages and disadvantages to the base 2 system. The advantages are there's only 2 digits. So that's something that a radio can handle, because you can represent a 0 and a 1 very easily electrically. Ground as a 0 or a low, voltage being present is a high or a 1. That's really simple to do, and you can do that with a switch. Microprocessors, anything, but they can do that. Either apply a ground or a voltage to a pin, and that's why they use the base 2 system or the binary system. Binary is made up of just that, 0 and 1. That's it. Now you can make up any number with just that, a 0 and a 1. The problem with binary is the bigger your decimal number gets, the larger your binary number gets exponentially. It gets huge. Binary numbers get enormous really quick. So I like to describe this column up here. So I've written down weight. So in binary, what we're doing is we have, and when you see binary written, those zeros and ones, the way it's normally written is what's known as the most significant digit first to the least significant digit last. Now, unfortunately, if you work on CB radios, get used to everything being backwards. And I'm going to show that, there are 3 things that are backwards with this radio we're working on here. Yeah, I don't know why manufacturers had to do that, but yeah, there's some engineer that should be smacked upside the head back in history that did this. But in any case, but you can see here, so this would be the least significant digit. This is a 1, and we have 2, 4, 8, 16, 32. And then depending on how big of a number we're trying to make, this column would just, continue out to infinity. It just keeps on going. It's going to be 1, 2, 4, 8, 16, 32, 64, 128, 256. And 256 in this radio is the most significant digit. That's the highest pin in this radio, and we'll show that. So how you actually count, or how you convert a number from decimal into binary, it's actually really simple. It's just an addition problem. That's all it is. I'm assuming you can probably add and subtract. So if you can add and subtract, you can do binary. It's that simple. Now, over on this left-hand column, I have decimal numbers. So using this system up here, from 0 to 9. Over here, underneath of these columns, you're going to see the 1s and 0s. That's the binary. So a decimal number 1 is 1 in binary. So we put a 1 in this column. If we wanted to make up the number 3, we would have 1, 1. And here's where you can see the addition comes in. So what we did was we have a 1 in each of these columns. So that basically means that whatever number that column represents, or its weight, is added into. So 2 plus 1 is 3. If there was a 0 here, so if we had 1, 0, it would be 2, because it would be 2, because there's a 1 in the column. And if there was a 0 here, well, that would mean this didn't count, so it would be 2 plus 0, which is 2. If we get to 4, and we can start to see our problem, we've only increased from the decimal number 1 to the decimal number 4, and we're already out to a 3-digit figure here. That's what I said. Binary numbers get really big really fast, or they get really long really fast. But that's only because we only have 2 characters. We don't have 10 to pick from. But you can see, for a decimal number 4, we would put a 1 in the 4's column, a 0 in the 2 column, and a 0 in the 1 column. So it's 4 plus 0 is 4. If we get to the number 7, that would be 1, 1, 1 in binary. 4 plus 2 plus 1 equals 7. 10, somehow I forgot to write 10. How the hell did I do that? Well, we can just write 10 really quick here. 1, 0, 1, 0. There, just that simple. Now we've created 10 in binary. 10 is 8 plus 2. The 4 and the 1 are not used. Just that simple. But again, see that? We've done come out another column. If we take a number like 54, we need to come out to the 32 column. So it's going to be 32 plus 16 plus 4 plus 2 equals 54. It's just that simple. That's all there is to binary. And like I say, if you had even bigger numbers yet, you're just going to have to continue out here. And these are, if you notice, this weight I have written up here, they're multiples of 2. So it's 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. And like I say, it would just continue on just like that. The next column, if we had to make an even bigger number, would be 64, because 2 times 32 is 64, times 2 is 128. And like I say, for this radio, the highest or most significant digit that's used with this PLL is 256, which is 128 times 2. So now an easy way to learn to write binary is to do just that. Write it, and write it a lot. So the best thing to have if you want to modify radios, let's say, and I have an example set up over here. You can see I have a little switch box here. This is a little test box that I've had for, God, forever, it seems like. But it's wired up in circuit to do channel modifications, and I'm gonna show that. But the best, probably the most important thing is to either have a data sheet or some type of printout for the PLL that you're using. So right here, I picked this up online, free, just download and print it, or just print it. I just printed the page, but this is on the Radio Mod's website. He has a really good website, but the main thing is he has basically all of the popular PLLs on that website, and it goes into a lot of detail about the PLLs. How, one of the most important for you if you're going to do something like this is to have the pin out, because you need to know what each pin on that IC is. But he gives the mixing schemes, how they work, all important. Down here we can see it actually tells you what each pin is, what its job is. Now the important ones for this demonstration are going to be the programmable input or binary pins, and I call those the program pins. So you can see pin number, and when I say pin number, and this is where I say things, there's a lot of things that are backwards. This is the first thing that's backwards. So let me just reach over here and find one. Okay, here's some ICs. These are not PLLs, but the pin number, when I say pin number, I mean the physical pin on this IC here. So there's an identifier that identifies pin number 1, the little dot. So that's pin 1, and then it would count pin 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, on around. It varies how many, how long the IC is, how many pins it has. But that's the physical pin number. So when you hear me say pin number, that's what I mean. I mean the actual pin on the IC. Now there's what I call the pin identifier. That usually be like a 2 or 3 letter code or number, or letter and number code. And you can see it's P0 to P8 for those programmable input binary pins, okay? So I call those the program pins. But that's P for program, or programmable, but it's programmable pin 0 to programmable pin 8. So that's a total of 9 pins, because 0 and then 8 more pins. But you can see, here's the first thing that's backwards. The digits go the opposite direction. As you increase in pin numbers, the identification number decreases. Ugh. Yeah, it's just something to keep in mind. P0 is 15, 1 is 14. As this number is going up, this number is going down. One thing to remember. It's not a problem. You have the data sheet or a sheet like this where you can see that. The other thing, if you're working on a radio, so here's a chart. See, this is all off the same website, but this is normally known as a programming chart, or like a service manual for this radio over here, an encode frequency correlation chart, or if you're using a SAMS manual, and a lot of other manuals, they're known as truth tables. What these do is actually tell you, when you put the channel selector on the radio on a channel, they tell you what the programming is going to every one of those programmable pins on the IC. That's all this is. So you can see. Now we don't need to worry about the frequencies, because these charts usually also have your VCO frequencies, your mixing frequencies and all that. We don't care about that. What we want to know is basically the channel number, and of course the frequency that we're actually receiving and transmitting on. But there's 2 main digits we need to know, or it's nice to know. That's the N digital codes, or it's commonly referred to as the N code. That is the decimal number. Okay, we're back to this decimal versus binary. So this encode over here equals 330. Now, here's where it gets confusing again. And don't blame me. I'm not the idiot in the past that decided to write shit like this, but pretty much any CB service manual you look at, this chart, you can look at this chart, you can pull a SAMS manual out, almost all of them. Matter of fact, I don't know if I've ever seen one that was correct. The binary code in these books is backwards. What I mean by that is, Remember, I said when you write binary code, it's supposed to be most significant digit, meaning the digit with the most weight should be first, and the least significant digit, that's always going to be the 1, should be the last digit. This ain't like that. Don't blame me, blame the engineers or whoever decided to number these things or put it in these books. It's backwards. This is the least significant digit. Over here is the most significant digit. Now, another thing you'll notice in this service manual, there's actually 3 columns missing. The reason they didn't write, because you can see we have P0, 1, 2, 3, 4, 5. But remember, there's a P6, 7, and 8. Well, why aren't they here? That's because in this radio, for the 40 CB channels, those pins never change state. Physically, pin 9 and pin 8, which are programmable pins, P6 and P7, they are always a 1. They're always at the voltage. They always have voltage there. They're the same for all 40 channels. Pin number 7, which is programmable pin number 8, is always a 0. It's always at ground potential for all 40 channels. So they didn't even bother to write them in the book. These are the pins that change. Depending on what channel you're on, all of these pins will change state at some point in time. But like I say, the problem is the code is written backwards here. I think they did it because they're using what I call the identifier PO, P1, P2, P3. They did those in increasing value. They shouldn't have written it like this. They should have started it. If they were going to have PO 1, 2, 3, 4, 5, they should have written it in this manual as P5, 4, 3, 2, 1, 0. Putting the most significant digit first. It's just something to remember. Do that because it's backwards. Now, if you want to learn how to actually write and get, it's not so much to learn it. You've learned binary. It's like I say, it's simple. It's not that hard. But the best way to get proficient at it is probably what I should say is to write it. And an easy way to get practice writing it with something practical that you can use in the future is to make your own truth table that covers every possible combination for a PLL. Now, over the years, I have handwritten these out. Now, I know there's probably a program somewhere online to do this, but I'm a math nut. I like writing stuff like this. It's just that this is relaxation for me. Some people go do other stuff. They'll go to a beach. I'm not a beach person. I'd rather just sit and write binary all day. This makes me happy. Counting in binary. Yeah, I know I'm an oddball, but I have written one of these charts basically for most all of the common PLLs. The advantage is once I have this is a really handy little book because it has all 511 possibilities written out. And I say 511 because if you do the math, now in my book here, and this is another thing, if you're going to write one of these, I suggest you do like the manufacturers did. Write it backwards. I know that's not the proper way to write it, but the reason I write my charts with the binary flipped, so it's least significant digit first to most significant digit last, is because the factory did that in their service manuals. And very frequently, you're going to look at something like this, and let's say you wanted to get to channel 41. So, of course, the factory 40 channels, that only covers up to channel 40. But if I write mine the same direction, or flipped with the least significant to most significant, then I can just take my manual and lay it on top of this one. And I mean, granted, it's spread out a little bit farther, but the columns line up directly because they're written in the same order. So yeah, I write my manuals backwards. That's just the way I do it because the manufacturers do that. All the manufacturers. Now, what I have written here is across the top, I have the weight for each of the pins. So you can see 1, 2, 4, 8, 16, 32, 64, 128, 256. I have the pin ID. So P0 through P8. I also have the physical pin number, so pin 15 through pin 7. That's the actual physical pin on the IC. I have the decimal number, or the N code, written over here on the right, and then the binary number for every possible channel, or every possible N code is written over here in binary. And you can see I started at 511. I started at 511 because that's the most numbers you can come up with using this many pins, okay? Because it's, if you add 256, 128, 64, 32, 16, 8421, if you add all those together, guess what you come up with? 511. That's the highest number you can create using that. And you can see in binary there is a 1 in every single column because every column is used. And then this is written out. There's, I think, like 13 or 14 pages of this. Okay, goes the whole way and starts with 1. And you can see a 1 is 1 and then all zeros. 1 in the least significant digit column, so would count as a 1, and then nothing else. So yeah. But if you do this, if you were to pick a PLL, and probably the best ones to pick if you work on vintage radios is going to be either like a PLL02A or a UPD858. Those were the two most popular PLLs in history. They were used for a long time. Millions and millions of CB radios out there have those, either one or the other of those PLLs used in them. But if you pick like the PLL02A in the case of this one, if you write out every possibility in decimal and in binary from 1 to 511, trust me, by the time you get to the end, you will really understand binary counting really well. You will have seared that into your brain. You'll never forget it. It's one of those repetitive, being repetitive. That's why when you went to school, you always had to keep doing something and doing something and doing something, because the more you do it, the more proficient you get at it. Well, trust me, if you write out 511 decimal numbers and binary numbers, the decimals no problem, but by the time you get done writing out 1 through 511 in binary, you're going to get really good at writing out in binary. And like I say, I've done this for every popular PLL there is. And this chart is really handy, and I'm going to show that when it comes into using like this little switch box over here for playing around trying to get those extra channels. So let's see, let me just take a break here real quick. I can feel in my throat, don't want to start coughing. I need to go fill my coffee cup up, get a drink. I'll come back and we'll actually take a look at the radio, and I'm going to explain what's actually happening when you're doing a channel modification and how you do it. So give me a second and I'll be right back. Okay, so I'm back now, all refreshed. So if you want to do modifications, and it may not just be to get extra channels, you may be trying to take a radio, because it used to be really popular back in the day, but some people still do it. They will convert CB radios into 10-meter amateur band radios. Amateur radio operators are doing that to use the radios on the amateur band. You can legally do that. Now, there are different ways of modifying a radio for different frequencies than they were originally intended for. You can change the crystal. So there were modification boards, Expo kits, that's what they were. The Expo kit usually came with a switch, and it had 3 crystal sockets on a little board. The center one would be empty, and then there would be 2 crystals on the outside sockets. That was for 40 additional channels up and 40 channels down. And then what you did was you took a crystal out of the radio, put it in that center socket, and then ran some wires down. Never liked those things. Those wires have all kinds of inductance and capacitance, and just the radios become unusable on sideband because they're unstable. You can do what I've got hooked up here. Just using toggle switches, you can get extra channels, because you can change the frequency, because that's what you're doing, remember, when you turn the channel selector down here, you're just changing the binary programming to the PLL, and that's nothing but a ground and a voltage source. You can use microprocessor boards like the Channel King boards that I use. There's other boards out there like the Digimax Lite, there's Lescom's board, there's a guy in Germany that makes a board. You can make your own board. You could do something kind of in between if you wanted to use like binary adder ICs. You can do stuff like that to get additional bands. And actually, speaking of binary adders, that's how Ranger and a lot of the Galaxy radios you'll see. Those radios that have 8 bands, it's usually a 4-position band selector switch, and then there'll be a high-low switch. That's actually how they get all 8 of those bands, is with a binary adder board, and it just has 2 binary adder ICs on it. But there's lots of ways to do it. This is the old school way, toggle switches. So what are you doing with your toggle switches? Well, if we look in the book here, because this is where this comes in really handy, because this chart only shows channel 1 through 40. Where with this, if I know the existing encode for any channel, I can just grab this book then and look it up in here, and then go in either direction to the limit, you know, of possibilities with this book, because I have it all written down. And how can you find that if you don't have a service manual? There may not be. Well, actually, this radio here, honestly, there is no service manual for this. This service manual is actually for the base station version of this radio. It is a rare oddball radio. It's a DAC. But it's basically the same as what was used in the base station radio that had a vacuum tube driver and a final. This one, on the other hand, is a full solid state radio. It has a driver and final transistors. But so I can use this truth chart, because the rest of the radio is still the same. But if you didn't have this book at all, no book, all you would need would be something as simple as a logic probe. Yes, the humble logic probe, thing most people have relegated to the rubbish bin over the years because they think, well, why do I need a logic probe? Well, for stuff like this, it's actually really, really handy. So if you did not know what the binary programming is for a radio, you can make your own truth chart. If you don't want to write out a whole book like this, that's fine, but you could make up a chart like this. All you would need to do is find out what the binary code is for one channel. That's it. Because once you have it for one channel, it just counts either up or down from that point. And there's another one of those forwards and backwards things, which I'll get into in a second. It's a unique thing kind of to the PLL02A. Where'd my pointer go? But with the logic probe, all this thing does, and I have it hooked up to the radio over here. Let's bring this over into view. So what all do I have set up over here? So I've got a radio. This radio had a bunch of channel modifications already. I've just temporarily installed this just for this demonstration. I picked this radio because I had it already torn apart, been in the process of restoring it, and figured, well, if I'm going to try and explain channel modifications, why not do it to one that already had all the circuit traces cut? So it was really easy for me to modify this radio without actually having to modify it, because it had already been done. All the traces were already cut to all of the pins, through all these wires, and that's what these wires are here. So you have the channel selector switch, has a ground attached to it, and has a positive voltage source being sent to it, and then that either voltage or ground is then what's attached, is getting sent through these wires to the program pins. So that's all these are. That's it. Ground or voltage. That's all. And that's what the logic probe checks. High is a 1 or a voltage. Low is ground or 0. And then what you can do is take your radio, put it on, pick a channel. Usually you'd start with channel 1, but put the radio on channel 1. You just take your logic probe, or let's say, actually, what am I on here? And yeah, there's missing digits on this display. This is actually channel 16. So if we go down to channel 16 here, we can see we should have 00, 11, 01, and then remember, these last 3 digits just carry down because they never change state. So it'd be 110. So the first 4 should be 0011. So if I check, I should see 0 or a low, 0, 1, 1, and then we have 0, 1, 0, 1. So we know all the programming coming from the channel selector switch is correct. That was all these digits. These never change. This pin here, which is always high, okay, that's pin 9. Then we have pin 8 over here, which is always high. And I'm never going to get, without getting my head down in here to see it. Well, no, actually I can just touch it over here. It's actually where it comes from. That tests as a low. That's actually pin 7, okay? But like I say, with the logic probe, you can make your own truth chart. Stick the radio on a channel, buzz out, each of the pins and see what their state is and write it down. If you're having a problem, you don't know, maybe your channel selector switch is bad. Some channel selectors back in the day, and even actually into fairly recent history, had those little flat flex style cable. It wasn't really a circuit board like this one down here. They had that flat flex cable, which those things are fragile. And they commonly get circuit traces, will get broken on those things if the radio's been apart a couple times. With this, you could troubleshoot that. You could put the radio on whatever channel, look in your service manual, see what the programming is supposed to be getting to the PLL, actually test it down at the circuit board and see if it's the same. If what you're testing at the pins of the PLL matches what you're seeing on the matches the truth chart, and the channels still aren't right, you either have frequency synthesis problems, like a crystal is, somebody may have done a channel modification, they may have put a different crystal in the radio, could be a bad PLL chip, but you diagnose from there. But you would have confirmed that your channel selector is okay. Now when you do modifications, all you're doing is, when you want to get extra channels, you need to intercept basically the signal, which, remember, the signal is nothing more than either a ground or a voltage being applied to those pins. But you need to intercept that, what's coming basically out of the channel selector, before it gets to the PLL, and then you can apply either your ground or your voltage source. And that's what I do with this little box. Now this little box I've had for years, made this thing up a long time ago. Doesn't need, and you can make one of these up, they're handy to have. Just take a little project box, doesn't have to be a Bud aluminum box, I just like them because they're indestructible. I only have 6 switches in here, because usually that's about all you'd need to really play around with usually. But there's 6 switches and there's 8 wires that go in and out of this box. There's 8 wires because I have 1 wire attached to each of the center terminals on these switches. So these are 3 position switches. Now actually these things are like ungodly expensive. They're gold plated pins with, I think they're platinum plated contacts, or they're mil spec toggle switches. You don't need to use anything like this. And they even have the little lock mechanism. You could just use some cheap Chinese ones, would be fine. But these are 3 positions, so it has, and the way I have it wired up, the red and the black wires, what those do is those get attached to the ground, and whatever the voltage source that's being used basically on the channel selector, whatever the logic level high, whatever that voltage is, that's what I pick. Okay, so that's what's applied to this red wire. So I'm sending a voltage source and a ground source into this box. That voltage is then applied to all the terminals on one side of each of the toggle switches, and then the ground is applied to the terminal on the opposite side to all of the toggle switches. And then the center terminal on all of the toggle switches gets a separate wire. Now I have, and you can get these little wiring harnesses on eBay, cheap, you can get them in different lengths. They're used for prototyping and doing stuff just like this. Originally these had male pins, okay, on one side. You see there's a pin sticking out of that, and then it's a socket on the other end. And what I've done is I've cut all the ends off of one set of them, stuck them. These are ribbon cables. All these wires are, one basically. But I cut the ends off of one. Those are the ones that are soldered to the connectors. The reason I don't solder those pins down is eventually they're going to wear out from soldering those pins into circuits and whatnot. So I use a second set of those cables, plug them into these, and that way if this end ever wears out, or over the years the cable gets shorter and shorter, I can just pull these, unplug them, plug a new set of cables in, and I never have to open this back up again to service it, to put new wires on it, because this end isn't really ever going to get damaged. It's this end down here. But I've got 2 of them aren't being used. But you can see, now, if you make something like this up, what you can do is, and it's what I've done here, anytime I use one of these, I've got to find the edge here, I just take a piece of transparent, it doesn't need to be transparent, it can be any color tape for that matter, but I just take a piece of tape and put it on the box, and that way I can then take a Sharpie and write on here what pins each of these toggle switches is attached to. So I know this toggle switch is attached to pin 11, this one to pin 10, this one to pin 9, and this one to pin 8. And then when I'm done doing whatever I have to do, I can just pull the tape off, throw it in a trash can, put the box back on the shelf, Next time I need it, I can just put 2 new strips of tape on there and write on the box, because it may be different pins, or I may be using this for a completely something different. It might not even be PLL related. Little switch boxes are handy to have sometimes for just doing troubleshooting and building projects and whatnot. But like I say, if you just put tape on there, then you don't have to try and rub it off of your box. It's just easy to just pull off and throw away when you're done with a project. But down here in the radio, you'll see that I don't actually have these wires soldered down to the pins on the circuit board. There's actually resistors just kind of come up over, and they're just looped in and soldered down to the circuit. And that's what you'll usually see in a radio. When you open it up, it has channel modifications, you'll usually see a resistor. What that resistor is there for is, these are 3.3K or 3,300 ohm resistors. The reason they're there is, remember, you're going to be intercepting what's coming out of this pin, so out of this channel selector switch. So let's say this yellow wire right here. Well, if it's sending a logic level high or a 1 to the PLL, that means there's voltage present on this thing, okay? If you just take a wire and attach it to ground there, well, you just now created a dead short. And you're going to let the magic smoke out of something, either out of your box, out of the channel selector switch, or something in the radio. You're going to let the magic smoke out if you go touching positive and negative together. We don't want to let the magic smoke out. So that's what this resistor does, okay? What you do is you cut the circuit traces, which, like I say, this one had all of the traces cut. But you cut the circuit trace, you jump across that cut with a resistor. In this case, like I say, I'm using a 3.3K resistor. Okay, so when the voltage, if this box, let's say, and the way I have this set up, okay, in the center, that's why I use 3 position switches. In the center, these wires are not attached to anything. They're not attached to the positive or to the negative. When I flip the switch up, that's a logic level high. Kind of makes sense, up high, and down low. Up high and down low is kind of the way I look at it. So that's a 0, that's a 1, okay? Switch is up, it's in the high state, it's supplying a voltage. When I put the switch down, it's a 0, a low, it's applying a ground to the pin. But like I say, if we didn't have this resistor in here, when I'd flip, let's just say that yellow wire had voltage on it, and let's say this, that's going to pin 11. Well, if I flip this switch to low, well, that has this tied to ground through this wire. That's a short. So what you do is you put a resistor here, okay? You have voltage, whatever this voltage is present on this side of the resistor. But now it has to go through a 3300K resistor. Now, when your switch box is turned off, basically, the switch is in the off position, the voltage can just pass through that, and that's plenty to turn on, for the logic level set to be either high or low on that PLL. But if you attach the wire that comes from your switch to the other side of the resistor, so you've got the voltage source on this side, comes from these wires, goes to one side of the resistor. On the other side of the resistor, that's where you would attach your toggle switch wire. It gets basically attached to the pin of the PLL. Now, if you have voltage present here and you ground the pin, you're grounding it on the other side of the resistor. You are going to burn up a little bit of electricity in the form of heat through that resistor, because you've got ground potential on this side now and voltage source on this side, but you've got a fairly high resistance value in there. You've got, like, in this case, I've got 3.3K or 3,300 ohm resistors in there. So, and these don't even get to the point where you can feel they're hot. There's so little amount of power is being used. But that's how that's done. So that's what I have here. I've got 4 resistors in here. There's one here, 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 and here. I have the wires that are attached to the center contacts on each of these 4 toggle switches are attached to pin, conversely, to pin 11, 10, 9, and 8. Now, which switch do you need to switch to get extra channels? That's where something like this, your handwritten guide, will come in handy. So, there's a few other things I need to explain. This is an oddball PLL. One thing you're going to notice is, once I get back here, actually, now what I've done is this, this is the right one. I had the channel numbers written down here, and you can see I've got the frequencies written down over here. Here's our decimal numbers, or encode, and then here's our binary. You can see for channel 1, that is a decimal 255. And then this is the binary code for that. All ones except for a 0, the most significant digit. If we wanted to go down in channel, look what happens. The encode increases. But what happens when you go from channel 1 to channel 2? The encode decreases. So this is another one of those cases where things are backwards. Don't ask me why. The people that made the PLL02A, that's just the way they made it. But when you're actually increasing in channel, the encode and the binary are decreasing. Because you can see 1 is 255, 2 is 254, 3 is 253. So as this number gets bigger, this number and this number, because remember, these are both the same thing, just different forms, base 10, base 2, these are decreasing while this goes up. Now, this is actually a good radio to show where low channels are really hard to get in easily, I should say. If you look at the code, and this is something to look at when you're trying to do a channel modification, you're looking for similarities where there's a lot of the same thing. So if you look at what channel 1 is, okay, that's binary code 255. That's, like I said, all ones except for the most significant digit is a 0. Remember, the encode counts backwards here compared to the channels. So if you go -1, look what that did. All zeros and a 1. So what that means is, if you wanted to put this radio channel selector on channel 1, basically, flip some switches and get channel -1, you would literally have to put a toggle switch on all 9 pins. Because from channel 1 to channel -1, every single pin changes state from 1 to 0, 1 0, 1 0, 1 0, 1 0, 1 0, 1 0, 1 0, 0 1. You would need 9 toggle switches to do that. That's not practical. Going the other direction, however, going up in channels, is fairly easy. So if we continue on here, you can see I got from like 1 to 26. Oh, one other thing, in case you're not familiar, most people are that do CB, but if you're not, in the CB band there are skip channels. Way back in the past, there used to be, I think they were used for business band originally. They're commonly referred to nowadays as the A channels, and if I'm not mistaken, I think most of those channels are now mainly used for like remote controls, like cheap radio controlled cars and stuff like that. I think that's where most of these the missing CB frequencies are actually allocated to be used. But as you can see, there are channels missing between 3 and 4, 7, 8, 11, 12, 15, 16, 19, and 20. So there's 5 missing channels. So you actually go 1, 2, 3. Most people would refer to this as channel 3A, and then 4, 5, 6, 7, 7A, 8, and so on. But that's something to keep in mind when you add extra channels, doing it the switch mode way. This channel selector is basically a binary encoder. When you turn a channel selector switch, it's what it's doing. It's either going to supply the grounds or the voltages, okay? So these skips are going to continue. If you get an additional 40 channels above the normal 40 channels, it's also going to have these skips in the same exact locations. So for the normal CB band, there are actually 45 frequencies there. Only 40 of them are used on CB, but there's 5 of them that are missing. And that block of 5 those skips are going to carry over to the next chunk. So now if we look at what we're looking for though when we want to add channels is, so we can see, remember channel 1, all ones and a 0. So we want to try and find somewhere where there's a lot of 1s, because the more 1s there are, well, that's the less pins that we have to put toggle switches on. So if you look on here, you can see we'd come through. Here's the end of the CB band, channel 40, okay? That's 1100, 10, 110. Now this pin is never going to change state, so we really never have to worry about pin 7. It's just, no matter, yeah, it's by the time you would get to the point where it would change state, you would be so high, the radio's never going to cover. And that's another thing to remember. Radio like this is never going to be able to cover 511 possibilities that PLL, just because the PLL, you can flip some switches and get 511 different combinations, doesn't mean your radio is going to get that. You're never going to get it to cover 5.11 megahertz worth of band spread. It just ain't going to happen. But we can see, like I said, channel 1 is all ones and a 0. So if we come to the end of the CB band, well, what would be channel 41? 0, 1, 0, 0, 1, 0, 1, 1, 0. Man, there's a lot of zeros in there. You'd need a toggle switch here, a toggle switch here, a toggle switch here, and here. Yeah, that's just, ugh. Now, if you just skip forward, if you skip these 3 channels here, I don't know if it shows up in the camera, but I have written more lightly in pencil. I have 1H and then 2, 3, and you can see there's a skip. 4, 5, 6, 7, skip. 8, 9, 10, 11, skip. 12, 13, 14, 15, skip. 16, and so on, and then the 19 and skip. But the H represents high, and then actually we get to like the next page. I have 1HH, because that's high. High. But it's very easy if we skip 3 frequencies after channel 40. Look what happens at 27445, which is decimal number 207. We get lots of ones, which is what we're looking for. 1, 1, 1, 1, 0, 0, 1, 1, 0. So that means the only difference between what's coming out of that channel selector switch at channel 1, which is all ones and a 0, decimal number 207 works out to where only 2 pins are different, which is pin 11 and pin 10. So if we were to take pin 11 and pin 10, flip the switches down, we now have, this radio is now on 27.445. It's just that simple. And then you'll see, with just those 2 switches, if you leave those in that position, it'll actually stay the same for quite a while, actually till you get up to, I guess, channel 14, where we come back to this all ones again. So if we look at channel 14, we can see what's channel 14. 1, 1, 1, 1, 0, 1, 1, 1, 0. So 4 ones a 0, 3 ones a 0. What's channel 14 high? Continuous ones, 0, 1, 0. So there's 1 pin that would need to change. We got 14, this pin right here, which is pin 11. If you follow that up, that's pin 11. So that would mean pin 11 would need to be low. Pin 10 would need to remain, I put the switch back in the center because I don't need to supply the voltage. The channel selector is doing that. I just need to pull pin 11 low, and that's it. It looks like 14. Wait a minute, what's pin 9? I'd need to change the state of pin 9 as well. Pin 9 needs to be a 0 because it's 0, 1, yeah, there's 3 ones, pin 14, yeah. So, actually I had that backwards. I need to change the state high on 11, not low. It's the problem with talking and trying to do binary. Not a good combination. Yeah, pin 11 needs to be drawn high, and then pin 9 would need to be brought low. So yeah, pin 9 would be brought low, and that would get us 27605, and then the channels would continue again. But notice, see how there's all ones here, and then once you get up to a certain point, you get to a large block of, where the heck is it? Right here. There's a large block of ones. It's repetitive, because remember, this is counting, 1, 0, 0, 0, 1, 1. But you can just follow it. It's kind of at a slope here. So the lower codes repeat. You can see 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. It just repeats, repeats, repeats. If you come out to the next column, that's going to repeat again, but repeat more infrequently. But it just keeps repeating and repeating. So that's what you'll get. You'll get a block of channels. You'll need to change your switch state. You'll get another block of channels. You'll need to change your switch states again, and you'll get another block of channels. And it just continues like that. So in this case, we needed 2 switches one switch up, one switch down, where I think the first one to get channel 1, we had to do what? Put, I think, these first 2 switches down. But like I say, having this chart, that's all you got to do. You have to look at what's the channel selector sending out and what do you want. Whatever the difference is, that's what you would need to change with toggle switches. And it's just that simple. And I can show this actually works. So I've actually already written out a few here. Actually, just back down here to the paper really quick. I actually wrote down channel 20. You might be able to see it under the tape there. I can just pull it off. I don't need to hide it. The code's right. The problem is this radio can't get up this high to the 20 high or 28165. If I adjust the VCO voltage to where the PL, and this is another thing we're not going to get into, but just be aware when you're doing extra channels, remember, the PLL is not the only thing limiting channels in this radio. Getting your VCO voltage and your PLL to actually lock on a channel, well, that doesn't have anything to do with the programming pins. That has to do with the frequency and your VCO voltage, your voltage controlled oscillator, broadbanding, receive, and transmit. Like I say, there's just lots of other things to come into play. But as far as programming, I wrote this one down. Yeah, I can't get 20 high. If I set the VCO voltage to where the PLL will lock on 20 high, then CB channel 1 will not lock. So it actually, the highest I can get is like channel 16 high. So let's do these two. So I've written down the decimal, or the channel number. I've written out the binary code. Remember, this is backwards because we're going from least significant to most significant, but I have the pin numbers up here, so from pin 15 to pin 7, and then I have, remember, toggle switches here that are actually attached to, what, 11, 10, 9, and 8. So this one, this one, this one, and this one have toggle switches that we can change the states from high to low, back and forth. So if we start with, let's say, channel 36, so we'll start out with the switches all in the center. So that means the switches aren't doing anything. They are completely out of circuit with this channel indicator that's missing almost all of its blasted digits. That's another thing I gotta fix. 40, 39, 38, 37, 36. So yeah, that's actually 36. Like I said, this radio is a work in progress. So we look up at the frequency counter, we grab the microphone, key it, and you can see 27. Let me turn the clarifier because the clarifier is unlocked on this radio. I'll get the frequency up a little bit there so you can see, but 27.365, okay? And that's what channel 36 is, 27.365. Now, if we want to get channel 36 high, which is 27.845, we need to see, well, what's different? Same, the same, the same, the same. There's a difference. A difference, a difference, same. So we need to change the state of 3 pins. So if we come back down here, a little switch box, and we can see pin 11 needs to change from a high. We need to change it to a low. So I'll put 11 down for low. We can see the next one is pin 10 is a low. We need it to be high. So I'll put this one in the high position. And we can see pin 9 needs to change from a high to a low. So I'll put it in the low position. And when I transmit, it should be on 27.845. So if we grab the microphone here, 27.845. So there we have it. And all I did was flip 3 switches to get that. So let's say we want to do some super high channels. We want to get up into the 28 megahertz range. Well, and I have this one written out for channel 16. So let's put the box back to where it's completely out of circuit. So all the switches are in the middle again. We'll put the radio on channel 16. Once I find it. Okay, 9, 10, 11, 12, 13, 14, 15, 16. So yeah, that's 16, believe me, just missing digits. And we go up to the frequency counter there. And you can, if I grab my chart here, you can see channel 16 is 27.155. And you can see 27.155. Now, we want to go to the super, or the, what I call the high channels. So we want to get this radio now to 28.115. So we need, again, to look at the chart and see what the differences are. Same, 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 same. This one's different. So pin 10 needs to be, the channel selector's supplying a 1. We need it to be 0. So I'm going to take 10 and put it low. Pin 9, channel selector sending a 1. We need to supply that with a low. And that's it. With 2 toggle switches, now when I transmit, I should be on 28.115. So we'll go back up here again, grab the microphone, and 28.115. It's just that simple. So that's all there is to it. The old school toggle switch mods, that's all you were doing. You're intercepting what the channel selector is sending out, because remember, I've got the channel selector on channel 16. So the channel selector has a ground to ground, voltage, voltage, ground, voltage, 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 ground. And this is what we want. And to attain that, we just needed to change the state. In the case of this channel, 16 high high, we needed to change the state of these 2 pins from high to low. We did that with the toggle switches. That's it. That's all there is to it. It's not rocket science. So I hope this helped to clear up a little bit, explain it. Because like I said, I do occasionally get questions about that. People are like, yeah, I tried reading up on something and they were talking about binary and encode, and I don't understand it. That's what they're talking about. Binary is just base 2. You have nothing but 0 and 1. This is how you write it. Normally, like I say, it's backwards. This is the way it should be written, most significant to least significant digit. Every CB service manual you look at, you are probably going to see it written this way, where it's least significant digit to most significant digit. Don't ask me, that's just what they did. Other things to remember with certain PLLs, the PLL02A being a good example of that. When you increase in channel number, the encode and binary code are actually decreasing. Most other PLL chips, when the channel number increases, so does the decimal and the binary. Most all other ICs increase with an increase in channels. This is just one of those, and I'm sorry, that just happened to be the radio I was working on when I decided to do this video. But yeah, like I say, this one, and I'm kind of glad I picked this because it does point out, because this is one of the PLL02As, one of the most popular PLL chips ever used. There's millions of them out there. So yeah, it's just, that's one thing you need to be aware of, is some of them count up, some of them count down. I showed the easy way to do it with toggle switches. Like I say, if you do a channel modification, don't just go attaching a switch that has, voltage on one side, ground on the other, and you're just sending that straight to the PLL pin. Because when you turn the channel selector switch, you got to remember, the channel selector switch is also providing either a voltage or a ground to that pin. And if you apply a voltage straight to a ground, magic smoke's going to come out. You need to make sure that the traces are cut. You bridge that cut with a resistor. The wire off of your toggle switch will then go to the PLL side of that resistor. So that way, when there's either a voltage on this side being sent and you apply a ground to the other side, it's isolated through that resistor. That's what that resistor is doing. It's isolating it so it's not a direct short. It's still a short, but it's a short through a 3,300 ohm resistor, which effectively is like kind of canceling out whatever's coming basically from your programming of the channel selector switch. Let's see, something else I wanted to mention. Oh, channel selector switches. There are different ones. So in the case of the PLL02A, depending if it was an AM or an AM and sideband radio and from what manufacturer it came from, the programming that's actually coming out of this switch can be different depending on which one it is. So, just a post-it note I had to pull down that I've written this down on. There's 3 popular channel selector switches used with the PLL02A. Now for like the UPD858, there's another block of popular channel selector switches. If you get other ones, like for more modern radios that have like maybe a 1450-106 PLL IC, there's different channel selector switches used with those. But for the PLL02A, there were 3 main channel selector switches used. There were some other oddball rare variants, but there's 3 the most popular ones. And the encode, that's what I have written down here. So for the AM radios, there were two different ones. And what was being sent out, which remember, the encode is nothing more, converted into binary. It's either a ground or a voltage. But they went from encode 224 to 286 was one version. The other version was 330 to 286. Okay? And then in the sideband radios, they usually have, like this one, remember, channel 1, if we look at the chart here, remember, channel 1 has a decimal or encode of 255, which is exactly what this one has. And if you look up to channel 40 is 211. And again, if we grab the book here and we look, channel 40 is 211. So, if you wanted to do a channel modification, because remember, getting lower channels specifically out of this radio is going to be hard, because going below channel 1 requires changing, to get channel -1 requires changing the state of every single pin. But if you got an AM radio and you parted out one of these channel selectors that covers from 224 to 286, well, that channel selector is a lower in encode. Or if you wanted to go, the other direction, you wanted to just go with like a 300, because actually that's what you would need. You would need a channel selector switch that goes from, actually not 330 to 286, it'd be 286 to 330. I got one of those backwards. But yeah, the lowest number there, 286. But that's what you would need. Or like I say, you can use, there's lots of different ways of doing it. That's one method. You can pull a channel selector switch out of a different radio, play around with it. And you can use channel selectors even from radios that don't have a PLL02A in it. You would just need to buzz out those switches and see how those rotary switches in there are basically programming the PLL. You'd need to basically make up a truth chart for your channel selector switch, and then you would know that's going to be the truth chart then for the radio, because that's what that channel selector switch is actually sending to the PLL. Binary code, if you want to try and figure out numbers. Like I say, actually how you make a decimal number into binary. If it's a really small number, 1, yeah, that's easy. 1 is 1. 3 is easy. That's 2 plus 1, so 1, 1. You get out to 54, you have to start actually using some brain cells to figure out where the ones need to be. Okay, so 54. Well, the next number that's would be in the weight column here would be 64. Well, 54 is less than 64, so we know we can't. So we're going to have to use the 32. So you'd have to do 32 minus 54 is going to be 22. Okay, so you got 22. 16 is bigger than 22, so you'd put a 1 in that column. That would be 16 minus from 22. But you remainder, and then you got to come down and subtract 4. Okay, that's 2 left over, and then you can use the 2 here. A really, really easy way. Now, like I say, if you get up into numbers this big, in the 250s, you've got 9 columns you got to fill in. So yeah, okay, that's 252, okay, so that would be, let's see, 128 minus 64, and that's a lot of math. Get a calculator. If you're going to do this stuff with any frequency, get a scientific calculator. I think you can get this one in Walmart. It is cheap. I'm a Casio fan. I've got a few hundred scientific calculators. It's like anything electronic. I collect old stuff. I've got hundreds of old scientific calculators, but this is a current model, and I think you can pick this up in Walmart. And it's currently, I think, in Walmart, and I think even on Amazon and eBay, they're less than $13. They're like $12.80 or $12.90. It's really, really cheap. But this calculator has, and most good larger scientific calculators have this feature, but this one does. It's cheap and it does. And the magic that it does that makes this really simple is it automatically converts between decimal and binary. Actually, it converts between decimal, binary, hexadecimal, and octal. So, and I can show you that. So if we turn the calculator on, I actually already have it in that mode. Let me take it out. So this is what you would normally see when you turn the calculator on. This has a base N mode. So if I hit the mode selector switch, you can see it gives us all these options, different modes we can select. This is the one we're interested in, base N. So if we hit the number 4, it switches it into that base N mode. And you can see right there it says, and actually if you look down here at the keypad, you can see it says DEC, that stands for decimal, HEX, that's hexadecimal, BIN, that's binary, that's what we're concerned with, and OCT, which is octal. And the hexadecimal and octal are different, just like this is. So just like binary is different from decimal, hexadecimal and octal are different as well. Hexadecimal is what, a 16, God, I gotta remember, I haven't had to do hexadecimal for a long time. I think that's a base 16, and octal, I've never really had to use octal before. That's a different base system. But yeah, hexadecimal is a base 16. So actually, let me just see here. I can figure this out real quick. Was it 16, enter hexadecimal? Nope, that's a 10. So it's 15. The decimal should be F. Yes, okay, yeah, 15. So yeah, 15 is actually an F in hexadecimal. I don't want to confuse it. Let's get back to decimal. So, but with this calculator, so if you knew that you needed to get to like encode, let's say 255, or you know your encode is 255, you don't want to do this longhand figuring out where all these ones and zeros are. This calculator does it. Okay, you want 255, make sure that it's decimal and display. Like I say, if you hit decimal, hex, binary, or octal, it'll switch into those modes. But you want it on decimal, then you would just enter 255, enter. That moves whatever you typed in up there down here. So that now has recognized 255 as a decimal number, and hocus pocus, abracadabra, hit the binary number, bam, there it is. Now, remember, when you're looking at this calculator, this is the way binary is supposed to be written. Most significant digit to least significant digit. So that means this is the one, this has a weight of 1, 2, 4, 8, 16, 32, 64, 128. So it's backwards from what I have written here, backwards from what's in the service manuals. That's just something to remember. But let's pick something that doesn't have all ones and just a 0. Let's pick some oddball one like 236. Okay, so we'll hit clear. We go back to decimal, and let's type in 236. Enter. Okay, so we've now entered 236 as a decimal number. I just hit the bin or binary, and you can see that's 0. Now remember, I'm going to be reading from right to left because this is backwards. So, but 236, if you look down here, now while I'm reading it off of the page, you can look at the calculator, but remember, counting backwards, we should have, where was that? 236 should be 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, back down here, and then 1, 1, 1, 0, 1, 1, 1, 0, and then all the rest of them, and they have all these extra spaces. Those would be for even more significant digits, but they're not used. So, like I say, this calculator makes turning decimal numbers into binary really, really simple. And likewise, if you had a binary number and you don't want to sit here and add 128 plus 32 plus 8 plus 2 plus 1, you can just type in the binary number. So if you knew you had, let's just pick the first one up here at the top of the page. Now remember, when you enter it in the calculator, you need to do it from most significant to least significant, so I'm going to be reading from right to left. But 1, 0, 0, 0, 0, so 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, and then 1, 0, 0, 1, 1, 0, 0, 1. Enter. Okay, so that's now entered that as the binary. If we hit the decimal number, 265. If you look down here at the page, 265. So it can convert in either direction. And if you want to turn that decimal number into, if you're interested in the hexadecimal, that's 109 in hexadecimal or 411 in octal. But like I say, main things we're worried about are binary and decimal. So if you're going to do this a lot, doesn't have to be a Casio. Like I said, I just like these. They're cheap. They're readily available. Casio makes really nice calculators on the cheap that have a lot of features. And actually this calculator, the FX115 ES Plus, it's actually become my daily driver. I mean, next to my, well, actually I even just upgraded that recently. I've been using the little my little solar calculator for, God, over 2 decades now. I've had that other one for over 20 years probably. Casio just released this one not too long ago. This is the FX260 Solar 2. Okay, my original one was just the FX260 Solar. This is a new one. Now, don't go running out buying this thinking you're going to be able to do this stuff down here. This does not have the binary and decimal conversion on it, but I like this for a small shirt pocket calculator. Does a lot of stuff. And interestingly enough, Dave Jones just recently did a video on this calculator, and I did the modification to it that he actually came up with. I did use a different value than he did, but when you cover up, because this calculator is fully solar powered. It has no battery. This calculator is a two-way powered calculator, solar or internal battery. This one relies strictly on the solar power. So what if you were to get into the shade a little bit, where it's varying from, power to no, power to no power, power to no power. Well, what they have in there is just a high-value ceramic capacitor as a storage reservoir. Well, Dave found that where that is on there and increased it, and I did the same thing. I used a different value. I stuck a 47 microfarad tantalum capacitor in there, but look how long this will last with absolutely no power going in. And we're going to, let me uncover this while I'm speaking. I'm going to do the most mathematically complicated thing this calculator can do, and that's going to be the factorial of 69. 69, if I understand you're probably not a math whiz, or you may not understand what a factorial is, but a factorial is basically the multiplication of whatever number that is and every number below it. So let's say you had the number 4. The factorial of 4 is 4 times 3 times 2 times 1. The factorial of 69 is the result of 69 times 68 times 67 times 66, the whole way down to 1. It is an enormous number, and that's actually the largest number this calculator can calculate. So it's really hard on the processor though, so that's the point. It uses a lot of energy. And just look how long. When I changed that cap out to 47 microfarad, so I'm going to hit 69, shift, factorial. The hell? 69, shift, factorial. Must have hit the wrong button. 69, factorial. 69, factorial. I'm just going to keep doing it until it kills the storage charge in that capacitor. And remember, this thing's just running off with a charge in a little tiny surface. Oh, it's starting to fade. I can probably get it one more time. I can just see it there. I don't know if you can. I can just make it out, barely. But yeah, it's surprising, just upping the value of that little electrolytic capacitor in this little guy. Doubled or not doubled, it almost quadrupled, if not more, the on time of the calculator when there's absolutely no power going into it. But yeah, like I said, don't get this one for doing decimal to hex conversion. I just thought I'd show that neat little calculator. Like I say, this one, if you look at any calculator, like I say, it doesn't have to be a Casio, just make sure when you look at it you see the two things you would want to see to be able to do that is you need to have a button somewhere that has DEC. You need to see one that says DEC and BIN for decimal and binary, and that way you've got you'll have a calculator that can automatically do that conversion for you. Like I said, that's just really handy. If you're going to be doing this a lot, is to let a calculator do it for you. Better yet, like I say, write out a book, because you saw how easy it is. We know we need, if we wanted channel 40, high, or 40 high, we come over here to channel 40 high. We can just, it's real easy. I can just flip back from the page to page. I don't need to type it into a calculator or write it down on a piece of paper. I've already done that. It's all here in the book. And like I say, if you do something like this, this is really going to burn it into your brain how binary actually counts. Key things to remember: service manuals are usually backwards. PLL02A, as channels go up, encode goes down. most all other PLLs, as channels increase, so does the encode. That's just one of the oddities of the PLL. Also remember that usually the ID numbers are also backwards from the actual pin numbers. I swear they tried to make this as complicated as they could. It's the only thing I can figure. There's this good conspiracy theory for the conspiracy theorist out there. Yeah, they made this shit as hard to do as they possibly could to prevent people from doing it. But so I hope that helped. If there's something you didn't understand, maybe go back and rewatch that section of it. I think I pretty much covered everything from what binary is to how it's implemented, to the inputs at the programmable pins on your PLL, and how to intercept that and then supply your own voltage or ground. Like I say, it's just a matter of cutting the trace. So actually, let me just do that one last thing. Let me grab a scrap of paper here. So I'll draw a schematic representation of what we have down here. Okay, so let's say we have, here's our IC, okay, and we've got a couple pins on the IC. Okay, so there's a couple pins, and they're attached to circuit traces. Okay, those circuit traces, like in the case of that radio over there, they just come out to pads where those wires are soldered to. Okay, now all you're going to do is basically, if let's say these 4 pins were pins that you needed to change the programming states on. So what it would look like after you got done modifying it, you'd have your IC, you'd now have 4 traces coming out. They'd be cut, okay, and then remember, this end here goes off to the channel selector through these wires right here, from the wires down to the channel selector board. Oh, just drop my pen cap. Okay, and that's going to still be the same. On this side, you would still have the wires going off to the channel selector switch, but you've now cut the traces. And what you're doing is, I added a 3.3K resistor in series here, basically. That's it. Okay, that's all I did. Those traces were cut, I bridged them with a 3.3K resistor, and now what you would have would be your toggle switch. Back this out a little bit. So we'll just pick one of them. I'm not going to draw out all 4 of them, but you'd have your toggle switch, contacts, okay, you would have, and then you'd have your, okay, so that's the toggle switch where it actually flips. And remember, this one's these are 3 position switches, so this could actually, this bar right here is the part that flips, so it can actually be in the center. If it was in the center, it doesn't touch either contact, you know, and it's wire attached to each of those terminals. So these toggle switches have 3 terminals. One for the center, or the actual flipper, you can call it, if you want to call it that, and then there's the contacts, which are the 2 outside terminals on that toggle switch. But when you put the switch in the middle position, the flipper is actually straight out. It's not touching either one of those contacts. When you flip the switch in, and that's another thing to remember with toggle switches, when you physically grab, it's a pivot. So when you grab a toggle switch arm and you push it down, the actual arm inside the toggle switch is actually going up. It's going the opposite direction because it's on a pivot. Just something to remember. So when you put your switches in to keep them in the proper orientation, when you push a switch up, the arm inside, it's going to the bottom contact. When you flip a switch, toggle switch arm down, the contact inside the switch is actually going to the top contact. But, you know, in this case, what we'd have would be one of these would go off down to circuit board ground. And that's it. And then the other one, so wherever your voltage supply, you again look at your, you know, pull the data sheet, or you can go to the, you know, like the Radio Mods website and pull down the chart for whatever PLL you're working on. But this other one, what you'd want to do is find the pin on the PLL chip that is the voltage supply into the PLL, and that's where this other line would basically go to. You'd tie that to that one. So that's your voltage source or ground source, and then the toggle switch here, that wire would then come over and attach right there. Because remember, I said that gets attached to the side that's closest to the PLL. So now if you were to take this toggle switch, just actually as I have it in the picture, it's applied the toggle switch is in the grounded position. Okay, so that's now supplying a ground to this pin. But if the channel selector switch was applying, let's say 5 volts positive here, okay, there's still a 3.3 K resistor in isolating that 5 volts from that short to ground that you've attached. So you're applying a binary 0 here. The channel selector is trying to apply a binary 1 by applying voltage here, but it's not a dead short. No magic smoke comes out because there's a 3.3 K resistor here preventing that direct short. So that's all that is. That's all you're doing with the toggle switch. And like I say, that's also why you have the resistor there, is to prevent the magic smoke from coming out. So the ground and the voltage sources never come in contact directly with each other. I think that ought to pretty much cover it. Like I say, if there's anything you didn't understand, maybe go back and rewatch the section. That pretty much covers decimal, binary, what it does in your PLL, how to get into it and modify it, how to count in binary. Like I say, things to remember that are gotchas. The things that will easily get you when you start doing this kind of stuff is, don't forget to skip channels when you're trying to make up a channel chart and whatnot, or you're trying to get banks of channels. Don't forget there's this channel selector switch, the contacts in there, they're just fixed. The channel selector switch is what it is. It's a 45, there's actually 45 basically slots, but there's only 40 positions because it skips the binary or the encode for these 5 channels that are used for other things. Like I say, nowadays I think it's mainly like remote control cars and whatnot. But yeah, don't forget those. If you're working specifically on a PLL02A, don't forget the code counting backwards, the pins backward. Yeah, there's just all these things are backwards. But like I said, if you play around with it, what you should do is probably just go find a good working radio. Well, it doesn't need to be at a good radio, but a working radio that has a modifiable PLL. It's just a junk radio though. It looks like hell. It's an AM radio, has no real financial value. You know, the covers are rusted in half. But as long as the radio works, play with it. That's the radio you want to experiment with. Make yourself a little box. If you plan on doing this a lot, it's actually nice to have these. Like I say, that's why I have these. The boxes are nice to, that way when you, just because you looked it up on the chart and it looks like, well, yeah, that's all I should have to do is apply a switch here, 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 and here, and it should work. Try it. The last thing you want to do is go through doing a modification like that, adding switches, spending all that time wiring everything up just to find out that you had something wrong because you might have forgotten the skip in the code for channels, or you missed something. If you do it with a box like this, you can try it first. Look at, if you have a frequency counter, you can then look over and actually transmit and look at the frequency counter and see, okay, it's on 28115. Well, is that the channel you actually wanted? If not, then you can find your problem, but you haven't hardwired it into the radio yet, or you haven't made up a permanently mounted external switch box, which is what I do. And that's another thing. I personally do not do channel modifications using these switches. I just won't do it. I have to undo that crap so frequently. I get radios, like this radio, it's got channel modifications. And people want those out, because I usually am not doing those kind of modifications. I'm usually the guy that has to remove this shit. I know I just showed you how to do it, but yeah, I'm usually the guy that ends up getting stuck removing all of that. I recommend do not use these switches. The reason I say that is, sometime down the road, well, you might not want those channels in the radio, or you sell the radio, and that's where the problem is. The radio gets sold to somebody else. They don't want the extra channels. The radio gets sent to me. Trust me, it is an absolute nightmare trying to rewire 3-position switches when someone has cut all of the wires out of the radio. They're gone. Now you've got to spend hours. It can literally take hours trying to trace out each switch contact to where it's supposed to be connected in the radio and get all that stuff hooked back up the way it originally was. It is an absolute nightmare. My suggestion is use something like this. Doesn't need to be a metal box, but you can get those little plastic project boxes, basically the same thing. It's got a lid, screws, 4 screws, whatnot, but get a plastic project box, get some cheap ribbon cable, It's really flexible, and you can see even like here, I rolled it up so I could put it through a round grommet. But do the same thing. Put however many toggle switches you need in the box, drill a hole, put a rubber grommet. You can roll up the ribbon cable, shove it in the hole. But if you use ribbon cable, what you do is you can make the cable any length you want, so it can reach out to the front of the radio, and and to mount it, what I usually do is I supply the customer with a piece of Velcro tape. That way they can stick it on the top or the side or the bottom of the radio, wherever they want the box. But you can take that ribbon cable, and it makes for what I call a no holes drilled installation. You don't have to rewire any switches, and you don't have to drill any holes in the covers or in the side of the radio or in the faceplate to add the toggle switches. What you do is you just run your ribbon cable in through the back here. You can see there's existing holes all over the back side of this radio. There's slots there. Well, you can just fish that cable in through one of those slots. Even if there's not a slot, the cable's really, really thin. You can just squeeze it in between the cover and this back flange. Run the cable up and attach it. You're done. 15, 20 years down the road, either you don't want the channel modification anymore, or the next owner doesn't want them. The only thing you have to do to remove the channel modification is take the cover off, desolder the ribbon cable from the circuit board, reattach the cut traces, modification's gone. Literally like 2 minutes. It takes 2 minutes to unmodify. Where if you do something with these switches, it can literally take hours to undo the modification. So save me a headache. Use external boxes. So I hope you learned something. I hope I didn't confuse you too much. I know binary can be very intimidating for some people. It's not if you do it. After you do it for a while, like I say, this is a handy way of getting familiar with it, is writing out some charts. But if you had trouble with it, go watch that section of the video again, maybe. And like I say, scientific calculators really help speed up life. They make it fast. So if you get one that can do your decimal to binary conversion. So I hope that helps. Get out there and work on a radio.